Hello, Math 151. We want to use calculus and graph y equals x cubed minus 12x squared plus 36x. In pre-calculus from previous math courses, we know that the domain of this graph is all real numbers from negative infinity to positive infinity. This is a polynomial of third degree, so it is continuous at all times. Okay, to find the x-intercepts, we know that set y equals 0 and solve. And if there is any x-intercepts, and in this case, there must be at least one because the degree is odd. So we have at least one x-intercept. And for y-intercept, let x equals 0. So in this case, the point 0, comma 0 is the y-intercept. Okay, well, the origin. Okay, let's go to next page and continue. We started with x cubed minus 12 x to the second plus 36x, and this was all y equals. Excuse me. So first, let's do for x-intercept. For x-intercept, set that equal to 0. I have x cubed minus 12x to the second plus 36x equals 0. I'm going to factor an x out of this. X times x to the second minus 12x plus 36 equals 0. And notice this is totally factorable. So here's x, x minus 6, and x minus 6 equals 0. So, which is the same as saying x times x minus 6 quantity squared equals to 0. Okay, so what are the roots? If I set that equal to 0, I get x equals 0 and x equals positive 6. Now, x equals 0, the multiplicity is 1. X equals 6, the multiplicity is 2. Because remember that we had x minus 6 quantity squared. This is the same as saying x minus 6 times x minus 6. So if I set this equal to 0, I have x equals 6 and x equals 6. I have it twice. Multiplicity is 2. What does that mean? That means, just a little review from pre-calculus, that at x equals 0, the graph crosses over. So I have a crossover at x equals 0 because multiplicity is odd. For x equals 6, multiplicity is even, so the graph bounces back. It will not cross over the x-axis. And we already said that the y-intercept is 0. Okay, let me go to the next page. How about asymptotes? Well, this is a polynomial. Okay, it is from left-hand side as x tends to negative infinity, f of x tends to negative infinity, and as x tends to positive infinity, f of x tends to positive infinity. So I certainly don't have any asymptotes for, once again, this is a polynomial. But now I want to know that I want to use the question, the instruction was to use calculus, okay? And what does using calculus do for us? Well, I do have a general shape of, since this is a cubic, something like this, okay? What does calculus help me? It helps me to find out this local maximum, find this local minimum right here, and find this concavity point of, that this inflection point. So notice, what do I mean by that? Notice that the graph is pretty much concave down for some part of this. It's concave down, and it is concave up for part of this. So this point right here, that the graph stops being concave down and starts being concave up, is known as point of inflection. And how do I find point of inflection? I'll take the second derivative and set it equal to 0. Once I take the first derivative and set it equal to 0, it's pointing out to my local max and local minimum, because the slope of the tangent line is 0. So the first derivative shows me where exactly those points are. And if you remember in Math 141, we ask ourselves, okay, where are those points? And we said that we have to wait for Math 151. So here it is. And to find the inflection point, we take the second derivative and set it equal to 0 and find out where this inflection point is. Let me go to the next page. So we said that f of x, we started at x cubed minus 12x to the second plus 36x. I'm going to go ahead and take the derivative of this. And so I have f prime of x equals 3x to the second minus 24x plus 36. And I'm going to go ahead and set that equal to 0 to find my local max and local min. So let's see, set equal to 0. Notice that I can pull a 3 out. So I have x squared minus 8x plus 12 equals 0. And I can keep factoring 3 times. So 2 numbers adding up to -8, multiplying to 12. So how about x minus 2 and x minus 6? Okay, equals 0. So notice that at x equals 2 and at x equals 6, I have a turning point. So at x equals 2 and at x equals 6, the slope of the tangent line is 0. So I have a turning point in there. Let me go to the next page. And so let's say, if I put a number line in here, if 2 is somewhere here, and let's say 6 is in here. If I choose a number to the left of 2, say 0, and plug that 0 into my derivative, that was, by the way, we said that f prime of x equals, we said that it was 3x squared minus 24x plus 36. Notice that if I apply in 0, I get a positive value to the left of 2. How about to the right of 2? Let's say if I pick a number, an easy one would be 3. 3 squared is 9 times 3 is 27 minus 24 times 3 plus 36. That gives me a negative value. So any values between 2 and 6 gives me a negative result. And to the right of 6, let's say 10. 10 squared is 100 times 3, so definitely it gives me positive. And notice that it is consistent with the general shape that we predicted in the very beginning, that to the left of 2, you see these tangent lines are positive. These tangent lines are positive. Then the tangent lines after between 2 and 6, the tangent lines are negative. Oops, And then to the right of 6, again, the tangent lines are positive. So let me go ahead and clear this. So I'm going to go ahead and write down that the function is increasing from negative infinity to 2, together with from 6 to infinity. And it's decreasing from 2 to 6. So I'm going to go ahead and go to the next page and all right. So I had for the local 2 and 6, I had it in here, and I had positive, negative, positive. So notice that if the tangent lines are positive up to 2, which is the root of tangent line is 0, and that then it keeps going up again. So I have local max at x equals 2. Well, maybe I better make that a little bit bigger so it's easier to see. Once again, remember that we said 2 is here, 6 is here. I got positive values here, negative values here, and positive here. So notice that the tangent lines are positive all the way on the left-hand side, but then they approach 0, and then they approach 0, and then they become negative. I had it backward, okay. So, and from in here, the tangent lines were negative, and then they changed direction to be positive. So I do have a local max at 2, and local min at 6. What are those points precisely? Well, precisely f of 2 equals and f of 6 equals. Well, let's see. If we plug in 2 into our main equation that we had, let's see, we get, putting in my calculator, I have a 32, and for 6, oh, I get, oh yeah, 0. Yeah. So I have a local minimum. So this local max, and local min. And it's going to be 2, 32. And this point like here is going to be 6, 0. So let me go ahead and find my inflection point. Go to the next page. And so we said that f prime of x, we had it as 3x forward minus 24x plus 36. And now what is f double prime of x? F double prime of x equals 6x minus 24. Set equal to 0. I have 6x equals to 24, and x equals 4. So notice that now 4. To the left of 4, any number to the left of 4, let's say 3 or 2 or 1 or even 0, gives me a negative value if I plug it into my f double prime. And to the right of 4, say 5, 6 times 5 is 30 minus 24, gives me a positive value, okay? So notice that I'm switching from negative to positive, so I certainly have inflection point at x equals 0. So at at x equals, at x equals 4. So when x is 4, and if you plug in 4 into our main equation, we get okay, 16. So at 4 comma 16, I do have an inflection point. So let me put all this together, and so I have, let me, this is x, and let me just use straight edge, and let's see, I had at 0, 0. All right, so the points that we had was for x-intercept, we had 0. Change colors. 0, 0 was 1 point, and we had 6 comma 0, 1, 2, 3, 4, 5, 6. Okay, and we said that a local, so here was 0, 6 comma 0, and this point was 0, 0. And we said that the local maximum was at 2 comma 32. So somewhere up here, 2 comma 32 was my local max. And remember that we said at 0, 0, the multiplicity was 1. It's odd, so the graph crosses over the x-axis. So this, at this part right here, I have a crossover and goes all the way to okay. But we said at 6 comma 0, the multiplicity was 2, so it is bouncing back. It is not, I do not have a crossover. And we said that at 4 comma 16, I do have an inflection point. So 4 comma 16, 1, 2, 3, 4, comma. So if that's 32 halfway somewhere in here, so that's my inflection point. So let me change. No, it's okay. I can continue. Okay. And notice that my inflection point right here, the graph is concave down in this part. And it is concave up in this part. So once again, just for the sake of discussion, remember we took the second derivative, we set it equal to 0, and the critical point was 4, and we tested number. Okay, we got negatives in here to the left of 4 and positive to the right of 4. So the graph is concave down to the left of 4, and it is concave up to the right of 4. I think this was a pretty good, not hard, like, you know, any cubic function is not that hard to graph, but I think it was kind of a complete example of showing how calculus is used to graph, to graph a function. Okay, thanks.